Good afternoon, ladies and gentlemen. Welcome to today's lunch hour lecture. I'm Jack Ashby from UCL Culture, and I'm here to welcome you and to welcome our speaker. But before I get on to welcoming Michel Tsamados, just say for those of you watching online and anyone in the room who wants to engage with us digitally, you can tweet at UCLLHL or follow and send your questions in on Slido with the event code 5282, and we'll get to your questions at the end. So today's lecturer is Dr. Michel Tsamados, who is a lecturer in polar observation and modeling here at the UCL Department of Earth Sciences. Much of Michel's research focuses on how sea ice behaves, both from the angles of material science and from the angle of climate science. And his work combines analyzing theoretical models and simulations, as well as looking at real-life data from the field. So he is perfectly placed to give today's lunch hour lecture, Are We Waking Up the Sleeping Arctic Ocean? If you join me in welcoming Dr. Michel Tsamados.
Thank you very much for coming. I am Michel Tsamados. I'm a physicist, and I've been working over the last 7 years on trying to understand the climate of the polar regions, and more specifically, the physics of the one component of the polar climate, or the climate of the polar regions, which is the sea ice. So sea ice is the frozen ocean, and also the ocean that is, the liquid ocean that is under the sea ice. So today I will answer this question, try to answer and address this question of, are we waking up the sleeping Arctic Ocean? So I should say that this, of course, is, as usual, most of the time with research, a collaborative effort between researchers at UCL, in the Department of Earth Sciences, in the Center for Polar Observation and Modeling. I have colleagues here as well. And the funding is coming from NERC, the National Environmental Research Council, and from the European Space Agency. So there will be three parts in this talk. First, we will look at how we have influenced the climate system, the climate of the polar regions. So this is our effect on the climate, and in particular how we have led to a retreat of the sea ice cover. Then we will try to address the question that I'm interested in, how are we waking up the sleeping Arctic oceans? So people have argued that we are performing the largest ever geophysical experiment in oceanography. By removing the sea ice cover, this region, this white region in the Arctic Ocean here, that really acts as an insulating blanket between the atmosphere and the ocean, we are really allowing the winds and the atmosphere to have a direct impact on the ocean, the liquid ocean under the sea ice. So the question I'm asking, are we going to allow, via our impact on the climate, to set this Arctic Ocean into motion, spin it up, and also are we going to allow the heat that is deep into the ocean, deeper in the ocean, to come at the surface and melt the sea ice even more? So this will be the second part. And then in a shorter third part, I will try to briefly discuss also how the climate, the Arctic climate itself, feedbacks to our mid-latitudes and to the climate of the planet as a whole. So in a nutshell, if you have one message to take out of today, is that the Arctic is not this remote place, and the climate of the Arctic impacts us all, and we also impact the climate of the Arctic. So let's start with the first part. How have we changed, humans have changed the Arctic in the last 100 years, and more accurately over the last 40 years. It's quite clear that the temperature of the polar regions, and in particular in the Arctic, has increased much faster than the average over the entire planet. So this shows the change of temperature between the 2000s and the average between 1950 and 1980. And while the average is about 0.6, 0.7 degrees over that 30, 40-year period, in the Arctic it's more than twice that. So it's almost 2 degrees warmer than it was in the 50s to 80s in recent times. So something is happening in the Arctic. It's called Arctic amplification. And the temperature rise in the Arctic is very strong, very rapid, and has a lot of effects. So one effect is the melting of the large ice cap over Greenland. So we're talking about 2 kilometers of ice that is slowly, that is melting. And the melt is potentially also accelerating, contributing to sea level rise. We have also glacier retreat throughout the Arctic continents. We have melt of the frozen soil, the permafrost, associated to warming and thawing. We have declining snow, rivers, and lake ice. But the topic of my talk is centered around this Arctic Ocean, the blue part in the middle that is in reality quite white because it's covered by sea ice. But sea ice is melting and the ocean is also warming. So this area is about the size of Europe, and in a sense, we are making it disappear. So there is a very direct quantifiable quantity we can come up with, and that was a paper that came out last month in Science from colleagues in the Center for Polar Observation and Modeling, Julian Struve, who showed that for every extra ton of carbon dioxide that we emit as humans in the atmosphere, we are melting 3 meters square of sea ice. So it's a very tangible way to quantify our direct impact. And for example, my trip in San Francisco next week to the American Geophysical Union will cost 10 meters square of sea ice. My iMac has costed sea ice 3 meters square. So these are numbers that are actually quite interesting to have in mind when we work on climate change. In a sense, and okay, it raises also political questions. My talk is purely physical, by the way, so for those who are into the politics of climate change, I will disappoint you slightly. So let's look at how the sea ice has changed from space, because what we are famous for at the Center for Polar Observation and Modeling is this beast, Cryosat. It has been flying for 6 years. It was a European mission originally proposed by members of CPOM. You have to know that the UK has a long history of polar remote sensing, starting in the 80s, possibly even late 70s. And this culminated into the successful mission that is Cryosat. Cryosat was designed to go and measure the polar regions of our planet. To measure, so this is an illustration of its orbit. It's orbiting at 700 kilometers height. And it's the satellite that goes the furthest to the north. So this little black hole corresponds to a latitude of 88 degrees north. So it was designed to measure as accurately as possible the thickness of the sea ice. So this white area you see in the middle of the Arctic Ocean, as well as the topography of the ocean. The ocean has highs and lows, valleys and mountains. And we were able, thanks to Christat, to measure this topography even through the sea ice for the first time at these latitudes. Also, it was designed to measure the changes of land ice over Greenland, but I won't talk too much about this today. So 6 years of amazing data. By the way, this corresponds to the period of my sea ice research. So I came in this group, and it was a very exciting time because the satellite was launched in April 2010, and I just joined a few months after, so I benefited a lot from this dynamic period of exciting data. So for a long time, it was the holy grail of polar research to be able to measure the thickness of the ice. So you have to imagine that you're trying from 700 kilometers high to measure a 20 centimeter elevation of ice, because it's a floating ice cube, and Archimedes' principle tells us that only a fraction, 10%, 15% of the ice will be flowing above the sea level, and we've been able to measure that and deduce the thickness of the ice. So these are the type of maps that we now have, thanks to Cryosat, of the ice thickness. So we know the volume of ice. And you can kind of see this pattern of thicker ice north of Canada and Greenland. And this is due to the transport of ice from Russia, due to the so-called transpolar drift, accumulating ice on this side, crushing it and piling it up. Another thing we've been able to measure is this topography I told you about, the sea surface of the oceans. So you have highs in yellow here in the Beaufort region. And we know, in analogy with the atmosphere as well, that if you have a pressure high or a pressure low, this will correspond to an anticyclonic or cyclonic circulation of the atmosphere, but it's also true in the ocean. Around the Beaufort High, you will have an anticyclonic circulation of the currents. So we know the currents as well, thanks to Cryosat and previous satellites. Before Cryosat, we have had information on the Arctic from other satellites from roughly 1979, the so-called satellite era. And this plot shows you an idea of how the extent has changed. So the average of the September sea ice extent, that is the minimum of the sea ice, on average, the yellow over the satellite era compared with the 2007 sea ice minimum is, again, conveying this idea that we are really removing the sea ice cover, this blanket of insulating ice on top of the Arctic Ocean. So what will happen? Another illustration of this removal of the sea ice blanket, of the sea ice cover, is this lovely animation, again, deduced from satellite observations, where we look at now the age of the sea ice. So the white parts are the older sea ice. So ice that is 5 years or older. The white parts, you can kind of see this seasonal cycle of the ice growing in the winter and melting in the summer. So in addition to that, you have a trend over the period from 1979 to today. And if I accelerate this movie to today, or let's say to 2016, you will probably agree with me that most of the older ice has almost totally disappeared. And you will actually see it clearly now. In 1984, 2016. 1984, 2016. So really, the sea ice we've removed with some quantifiers, such as the age of the ice has almost already totally disappeared. So the ice is really rapidly changing. Over my lifetime, it has, with some criteria, such as its age, almost totally disappeared already. This is summarizing this fact that the alarm bells are ringing in the Arctic and for sea ice. Top left is this decline of the sea ice extent. The maps are showing you where this decline has happened. Bottom left is the multi-year ice. The older ice has also completely almost disappeared. The thickness or the total volume of ice has lost almost 75% over my lifetime of its volume. And then as the ice becomes thinner and weaker, it is also more dynamic. You might have seen that the ice was moving around. It's not just a static blanket. It is a dynamic feature of our planet. And the speed of this, on average, of the sea ice has increased. This is a top right plot. And finally, the melt season, the duration over which sea ice is melting every year, has also increased. So really, we are removing this sea ice blanket. The question I'm asking is, what will happen on the ocean underneath? Are we going to allow the winds to really stir this ocean underneath, spin it up in a sense, allowing it to become more like a normal ocean? A normal ocean would be, for example, the Atlantic. Here illustrated the Atlantic, the North Atlantic. This is a numerical simulation from a high-resolution model run at Southampton, National Oceanographic Center at Southampton by colleagues. And you can, I think, quite clearly see that, of course, you have the western boundary currents, the so-called Gulf Stream, with speeds of 1 up to 2 meters per second, very wide. Now we're moving to the Pacific side, but you can agree that most of these oceans have quite wide features. And in comparison, in particular, to the Arctic Ocean up there, that is very quiet. So this is, I would say, very blue compared to the other oceans. And it is very quiet, again, because it has this blanket of sea ice, 2-meter thick blanket, insulating the currents from the wind above it. So if we zoom on the Arctic Ocean, then we can see that this blanket is dynamic. So again, satellite imagery of sea ice motion, and that there are two dominant circulation regimes. This curvy arrow is the Beaufort anticyclonic circulation that has been predominant over the last 20 years in the Arctic. And the straight line is the so-called transpolar drift. Both of these are wind-driven. And show you, for example, you can see quite amazing outflow of old, thick ice in the Fram Strait driven by the transpolar drift. But this shows that really the wind acts on the sea ice moves, and it's also the sea ice itself allows the ocean underneath to move. So we need to understand the three-layer mechanism to understand how if we are spinning up the ocean. By the way, this transpolar drift, Nansen, the explorer, the Norwegian explorer that tried to reach the North Pole in the early 20th century, took 2 years to cross the Arctic, roughly. Today, the same drift, the same transport, the same trip will take half the time. So the sea ice has become much more dynamic, much faster than it was. So colleagues from CPOM, from the Center for Polar Observation and Modeling, a few years ago, found that in 2012, that this anticyclonic regime was accumulating fresh water that comes from all the rivers of the Arctic, and the melting of Greenland and the melting of sea ice is accumulated due to this anticyclonic circulation in the Beaufort Sea in the middle of the gyre. This is something called Ekman transport, and it's associated to, it's a well-known oceanographic feature. And what they found that there was 8,000 cubic kilometers of fresh water concentrated in the middle of this topographic high in this gyre. 8,000 cubic kilometers is 9 billion. We worked out this early. It's 1 billion Olympic swimming pools of fresh water, And it's, in comparison, the Greenland is losing 300 kilometer cubes per year of fresh water. So you need 25 years of Greenland melt, assuming it remains constant, to equate to this volume of fresh water accumulating in the center of the Beaufort Gyre. So there is a question here, what will happen with this fresh water? And could it affect the general ocean circulation if it's released in the Atlantic, for example? We'll try and address that later. The point here is that what they didn't understand is why there was this accumulation of fresh water. Why more fresh water in the early 2000s? Because the winds didn't become more anticyclonic, not particularly more anticyclonic. So there must be another mechanism at play, allowing a more efficient way to spin up the ocean. And to understand that, you have to look at how the wind is transferring its energy, its mechanical energy, to the ocean. It does it directly on the open ocean parts of the Arctic. By blowing, it sets up waves. These waves are kind of rough, typically 1, 2, 3 meters high. And a rough surface will be more efficient at transferring momentum in the same way that if I push on the table, if it's very smooth, I'm not going to exert much force. But if it's rough, it will be easier to push the surface that I'm pushing on. So the wind is similar. It's blowing on the ocean, but it's also blowing on the ice itself. And again, the same idea is present here. If you have a rougher surface, then each of these obstacles on the surface of the ice, for example, this little hill is a little deformation of ice. Ice crushes and forms little obstacles of 1, 2 meters high. And when the wind is blowing on it, it really pushes on these things. And in the same way, it pushes on the edges of the ice. And similarly, the ice itself pushes on the ocean because the fluid flows around these obstacles is really pushed by the ice. So, and a rougher ice will be more effective, will have a better grip on the ocean underneath. So what we understood and we modeled is the fact that rougher ice has a bigger impact, will allow a more efficient transfer of momentum, of energy to the ocean underneath. So to validate that, I'm going to skip through this quickly, but we measured with colleagues from NASA the topography of the ice over 7 years of flight. So people from NASA have been flying airplanes and measuring the surface of the ocean, the topography. So these are the features I was telling you about, typically 1 meter high, and these are the so-called ridges. And we've been able to quantify a bit this roughness of the sea ice. Another way to quantify how effective is the wind at transferring its energy to the ocean and how strong is the interaction between the wind and the ice and between the ice and the ocean is to go in the Arctic itself and measure it. So this Professor Ian Brooks for Leeds went to the Arctic last summer for 6 weeks, starting from Svalbard through the North Pole. Seems like they went exactly to the North Pole for some reason to have fun. And then to the Canadian Basin and back again to Svalbard. And they measured the interaction between the ice and the ocean. That's probably him doing crazy things on top of on a mast. I should say I'm a modeler, so I've never been yet, which is very disappointing for you, I'm sure. But I want to go, but nobody wants to take me. So one day I will go. I'm also half Greek, so I'm a bit worried that I will struggle. But anyway, so the surface, different surface types have different roughness, as I said, and different interaction between the atmosphere and the ice. Rougher surface will be easier to move around, to push around. More fragmented surface has more edges, again, easier to push around. Melt ponds, so when there are little lakes covering the sea ice of melted sea ice and snow, it's also easier to push around. This, by the way, is an infrared camera that Ian had fun with measuring the thickness of the ice based on the temperature of the ice. Okay, another aspect of how we're changing the system is by removing the ice blanket, we're allowing the waves to become bigger and bigger. This is what this plot shows. So on the Beaufort region here, in 2012, we had these clear storms, strong storms that allow waves to develop fully up to 3, 4 meters high, 5 meters high, and contribute to the sea ice, to the absolute sea ice minimum at the end of the summer. So these waves did contribute to break the ice more than in normal years. And actually, if you think about it, as sea ice is retreating, we will have more and more of these strong waves emerging in the Arctic, in the new Arctic or the Arctic of the future. And this has also implication for coastal erosion of the Arctic region. Again, we're able to, thanks to Tom, who's here in the audience, measure the significant wave height thanks to the satellite measurements, thanks to Cryosat. again, some very exciting research coming there. So we see that and also more waves mean more effective momentum transfer potential in the future. Finally, the more direct, for this mechanical part, the more direct measurement of changes of the ocean is to measure the currents. And here I'm showing this average currents over the Arctic Ocean. And if we look at trends of this current, surface currents measured from a satellite, we see through different regions of the Arctic, gates. The orange, the green, and the blue gates show that there has been an acceleration of the current over a 13-year period. In 2007, in the southern Balfour region, there was a 5-fold increase of current due to the sudden retreat of sea ice. So we are trying to put the pieces of the puzzle together and trying to understand what will happen in the future in a sea ice-free regime. The third part on this is, are we going to wake up the ocean thermodynamically? Are we going to allow the heat that's in the deeper layers of the ocean, Arctic Ocean, to come and melt the ice even more? So far, we looked at the circulation at the surface, the blue arrows, driven mostly by wind, but actually there is a circulation in the ocean deeper, coming from the North Atlantic, warmer, saltier water. This is, in a way, a branch of the Gulf Stream coming all the way to the Norwegian Sea and penetrating in the Arctic Ocean. And this is diving in the Arctic Ocean below the fresh layer and lighter layers of fresh water that we discussed before. So there is this counterclockwise circulation of saltier, warmer water. It's only 2 degrees, but it's very warm relatively to the rest. And this releases its heat as it travels around the Arctic Ocean over several years. So there is this source of heat. There is also another source of heat coming from the Bering Strait. Again, warmer water penetrating in the Arctic Ocean. It doesn't dive as deep because it's fresher, it's lighter. So this idea of a stratified Arctic Ocean is quite important to have in mind. So at the top you have the blanket, the sea ice, solid, kind of solid layer of ice. Under it you have a 20-50 meter thickness of very well mixed fresh and cold layer of water. They're very light because it's fresh. You all know that saltier water is denser. Deeper you have the so-called halocline, a region of transition between very fresh and very saline water. And even further deep at 200-meter depths, you have the Atlantic water that's very saline and very warm. How do we know that? We have these things that are spread around the Arctic and go up and down at depths of the ocean, 700 meters, and measure temperature and salinity. So at the moment, it's very stratified, but it's changing. And are we going to be able to tap into this source of heat to melt the sea ice even more? This is an open question to some degree. More news related. Last week, we noticed that the total sea ice extent over our planet, both Arctic and Antarctic, was this red curve. We're talking about late November here. Normally, it's the time of the year where ice is growing in the Arctic. And here, over 40 years, I think the red curve is standing out. It's clearly an outlier. So something is happening that has stimulated the scientific community as well as the community more generally. Something is changing. Is the ice melting or not growing as much as before because it's melted from the top? Indeed, last week, on the 21st of November, we had this very warm Arctic atmosphere, temperature of more than 20 degrees above average. This is a pattern that's going to become more and more the norm in the Arctic. So the ice will melt from the top more efficiently. But also we have noticed in the past 30 years that this branch of warm, salty water from the Atlantic is becoming warmer and warmer and penetrates deeper and deeper in the Atlantic, in particular in this region of the Kara and Barents Sea up there. And this is precisely where we missed all this sea ice this year. So that's one of the reasons why we had this extremely low sea ice. And so we had actually melting at the end of November in this region. So normally the ice is growing. Here it was actually melting. So is it an early sign of the heat of the ocean melting it, or is it coming from the top? So there is a whole lots of all kinds of heat fluxes in the Arctic Ocean. I described the input of salty Atlantic water that releases some of the heat in the higher layers. In here, the region 7 is a region where the surface has been heated in the summer by the direct illumination of the sun. And some of this heat survived through the summer and is contributed to not allowing the ice to grow as much through the growth season. You also have input of Pacific water here that contributes more and more, according to observation, to melting the ice or to delaying the growth of the ice. And then recently people have also noticed that there is a intense heat flux at the continental shelf. So you have to be aware that the Arctic basin is half continental shelf, very shallow region, 50 to 100 meters, and then the Arctic basins are thousands of meters deep. At this transition region here, there is tidal mixing. So the tides interact with this slope and create very strong heat fluxes that again participate potentially to the melting of the ice. So all this is very current work, and we are trying to understand how this source of heat will be released. Are we waking up the Arctic Ocean thermodynamically? So how, just to conclude, how will this affect us? There are many, many studies on this. I will just give you a flavor. First of all, climate predictions over the 21st century predict that sea ice will continue to retreat, and the Arctic amplification of temperature will potentially even accelerate. So this is a result, for example, showing in red the temperature change by 2100 for different months. And you see that actually in the winter, November, December, January in 2100, in a scenario where we continue and increase our emission of greenhouse gases, temperature in the winter in the Arctic will grow by 20 degrees. So this is, I mean, it's a game changer in terms of the patterns over the Arctic. So this is highlighting that temperature increase per year, 0.2 degrees per year over 100 years is 20 degrees in the winter. So what does it mean for the weather? Changing the weather patterns over the Arctic will change the weather in the mid-latitudes. This for a simple reason. For example, in pre-industrial times, where the planet was as it was before we put all our greenhouse gases, there was a warm, of course, equator and a cold North Pole. Today, as I've shown you, or by the end of the century at least, the temperature at the pole, at the North Pole, is increasing much more rapidly than the temperature in the equator. So this gradient that is known to drive what is called the jet stream, this strong circulation of air at around 5-10 kilometers high at speeds up to 200 miles per hour that control to a large degree our weather patterns in the mid-latitude, will be modified by that. It is known that a weaker temperature gradient drives a slower jet stream and a more wavy jet stream. At least there is more and more evidence showing that. So this could contribute to a slower overall jet stream, more persistent patterns, weather patterns over our mid-latitudes in the Western Europe. For example, cold spells coming from the Arctic, and also more input of heat into the Arctic. So this is one way, feedback in the atmosphere. Another feedback is oceanic feedback. I told you that there was this huge volume of fresh water. Scientists have wondered for years, what if we put this fresh water somewhere else in the Atlantic? If some of this fresh water is released either here or here, okay, or here, but that's going to be longer. But these three regions are regions of where the circulation, the ocean is losing heat at a very fast pace. So it's warm water from the Gulf Stream coming into contact to very cold air. So you lose heat, you cool the ocean, and the ocean is cooler, denser, and falls to the bottom of the ocean. So these are really the drivers. These three regions are the drivers of the deep ocean circulation that I'm showing here, the so-called thermohaline circulation. So what would happen if we release this fresh water in one of these two regions, for example? What will happen? It will slow down. It will again act as an insulating layer. So you have this fresh, buoyant, light layer of water that prevents the deep water formation. So you could potentially slow down this circulation. And by slowing down the circulation, it could also impact the Gulf Stream and the weather patterns of Western Europe. So there are other feedbacks. For example, Greenland is expected to melt faster, create more sea level rise, and so on. There are many, many feedbacks. I'm only giving you here a flavor. So just to conclude, before I take a couple of questions, hopefully, we've seen 3 steps. We've changed the Arctic. The landscape is changing rapidly under man-made climate change. We've been able to measure this very accurately thanks to satellite over the last 40 years. I've addressed the question, are we waking up the sleeping Arctic Ocean? I discussed that yes, mechanically, and possibly also yes, thermodynamically. We are allowing the heat to come up at the surface more and more. And finally, I just briefly discussed the implications for us, for the mid-latitude people, for the Western Europeans. And I think I will stop it here and take questions. Thank you very much.
Thank you so much, Michel, for covering so much ground so clearly. That's a really enlightening talk. Does anyone have any questions in the audience down the front?
So you're talking about all these different things that can happen in the climate with the melting Arctic ice, and I know we're seeing like signs of increased flooding here in London. And I was just wondering what you think like the future impacts will be of the Arctic ice flooding, and what other weather impacts you think there could be because of this.
Antarctic ice melting?
Yeah.
Yeah, so here I focused on sea ice, and it's quite important. When I give similar talks, I realize that many people don't realize that sea ice and land ice is different. So land ice is 3 kilometers. In Antarctic, it's a 4-kilometer thick layer, so 4,000 meters thick layer of ice that is melting. But sea ice is 2 meters thick, so there's a factor of 1,000. So I didn't talk too much about land ice, I talked about sea ice. Sea ice melting doesn't directly contribute to sea level rise. If you melt your ice cube in your glass, the level will stay the same. But if you take another ice cube and put it in your glass, then there's sea level rise. So I didn't really talk too much about sea level rise, but again, that's one of the feedbacks I mentioned. If sea ice is melting, contributing to Arctic amplification, and the Greenland land ice will also melt faster. By the way, I think it's expected to melt, the timescales of melting is 1,000 years of Greenland ice, which would correspond to, I think, 7 meters of sea level rise. But the order of magnitude is within a timescale of 1,000 years, to give you an idea. Antarctica is 50 meters, but it's also harder to melt. But that's not why I talked about it. Yeah.
Thanks. There's a question just here. Can you just wait for the microphone so people online can hear you? Thanks.
It's a very nice talk. What about the connection between El Nino and these oscillations? That's a sort of popular subject now, so that the kind of climate skeptics are saying El Nino is going away, it's going to get cooler, and the Arctic ice is all going to return.
Good question.
What do you think about that?
So this is Julian Hunt. We were supposed to discuss before I gave the talk, and now he's asking me a tough question. To be completely honest, I don't know. This is the answer. This is not what I've worked on. I do work on projects on teleconnections, but I haven't looked at that specifically, this specific question. So I'm very keen to discuss this with you, but I wouldn't like to comment too much. Sorry. Yeah, you can say maybe.
Comment for the audience.
Yeah.
One of the interesting points is that now, you know, I used to be head of the Met Office, which and in the 1990s, the British weather forecast never talked about the jet stream. Well, they did in America, and now, of course, in weather forecasts, they regularly talk about the jet stream because we see this as a very strong phenomenon. And I think now understanding that and seeing why they have it over the UK or Northwest Europe, you know, it is a pattern that. But then there is a question of how that connects to the Gulf Stream. How about that question?
I shouldn't have invited Julian. So my understanding is that one pathway to impact to the Gulf Stream is by modifying the sources of deep water convection. So by slowing down this formation of deep water in this Gulf, Greenland and Iceland and Norwegian Sea or Labrador Sea, you might be pulling less water, in a sense, slowing down the Gulf Stream. That is my intuitive understanding. I'm sure there are other feedback processes to affect the Gulf Stream, but I wouldn't like to comment. I know you had a student working on the direct impact on sea ice on the Gulf Stream as well, the way it interacts with the Gulf Stream, which is something I'll be interested to discuss more with you.
There's a gentleman right in the middle towards the back.
Why do you have Arctic amplification? Where does it come from?
Okay, good question. So, so this is a pattern that has been seen in, geological times. Every time we have a switch from glacial to interglacial period, the regions that respond the fastest and that are important in changing this glacial phase are the polar regions, and the first to react is the Arctic. So the simplest qualitative argument is the ice albedo feedback. So this is one, sorry, it's the first slide, which is a bit, so, okay, there we go, sorry. So by melting the ice is white, it's reflecting the incoming solar radiation. By melting the ice, you make the surface darker. By making the surface darker, you create more input of heat. You warm the ocean and you melt more ice. So this is a kind of negative or positive feedback process that kind of catastrophically results to more melting. So this is one contribution. There are other mechanisms and feedbacks. Most of them are positive, but there are also negative ones.
Is there any more questions out there? Another one down the front.
In the beginning, I know you said this isn't about legislation or policy, you're not focusing on that, but for those who are into policy, how do you think we can bring science into that more? For people who doubt it, how do we bring about science into policy, and how do we have them work together in order to make those policies to prevent things like this from happening?
No, it's a good question. I mean, obviously, I don't spend a lot of my time thinking about this, as it's not my job, but maybe I should as a citizen, essentially. But some people have argued that instead of focusing on the physics, which is useless for you, you should focus on how it impacts our lives, which I think is a good argument. So how is climate change impacting my insurance policy and things like that, which I don't have, but whatever. So I think it's more, it speaks more to people than talking about the spin up of the Arctic Ocean. I think it will put them off, essentially. So probably don't come to my talks. Sure. Yeah. I mean, it's occasionally good to have somebody say Trump is stupid or something like that. Yeah. Or scientifically stupid.
Was there one question in the middle left? There, yeah. Yeah, sorry, go for it. Yep, please go for it.
Oh, okay, thanks. I think if something's clear from this is how complex this is, right? So in relation to the last question, just the difficulty of actually communicating this. But I was wondering, as a scientist, what do you think is, among the largest unknowns? Like, what do you think is the area of this that we really need to look more into that is not yet understood?
No, that's another good question. So I think being a modeler, I think improving the models, because the tools that we have to predict the future are climate models, right? So to have more confidence in those and to be able to say it, I think they are great tools, but to continue improving those would be an important step. And also to look in the past, including on geological times, we can learn things from longer time scales, because, and also just having more data, more observations, more research. I couldn't point on one specific, on my specific topic I could tell you, but I don't think it's necessarily covering the entire issue of climate change. And also, as I said, more implications for how it impacts people's life. Maybe a more direct contact with scientists would be good in that sense. But I'm a physicist, so I do the physics, but I'm happy to discuss with you're a geography, right? Yes.
Okay, I'm afraid that is all we've got time for today. But I want to thank you for coming. Thank you for your questions. And thank you mostly to Dr. Michel Tsamados.